So let me start. Thank you for coming. Welcome. And so, as Pavel mentioned, I'm sure that you forgot everything. So, therefore, today I want to just recall what we had before, more or less, and then we start new things. So, please then feel free to ask just very basic questions from anything that we covered before. This session is kind of for that, and so what's the business with that? So you zoom on this, or you yes, let's see. Da, da, dum. Thank you. So uh, I won't say anything about the definition of categories, functors, natural transformations. I assume that these are just known. If not, just let me know. Um, Therefore, I start just with the definition of topos, which is kind of the main thing that we like, right? So if you remember a category E, say, is called a topos, and usually it's also called elementary topos. Uh, if you have these three things, so first E has all finite limits. So I have to just recall what it means. So maybe. So limit simply means that you have a diagram in E, right? And finite means that everything is finite here. So the number of nodes and arrows, etc. And it's a diagram. So it could be something like this, that everything commutes, something big, small, I don't care. And then limit is simply just one node, one object here, such that you have a cone. Cone means that you have a map to any object here from this guy, such that any small triangle commutes. One, this is a cone, and limit is just the best cone, meaning that it's a cone. And for any other cone like this, you can factor it uniquely to that one. And we had some examples of this guy. If you remember, the obvious one is when this guy is empty. Then the limit is just one element. If you write down the definition, then when the diagram D, say, is empty, then the limit object would be just the terminal object, meaning that you have, this is the object, and for any other object, there exists a unique map to it. The other example that we liked is when the diagram here is just two nodes, two objects, say A, B. Then the limit would be what? Would be a cone, a best cone. So the best cone is just some object here, two maps. There is no map to commute. So, and this guy is simply just the product, we call it, right? And these are just the projections. And the universality means that for any C, any two maps to A and B, you get one unique map to this product. And the third one that we liked, kind of, was, maybe I have to go here, uh, is this guy. Three objects, two morphisms like this. And then cone would be one element, three morphisms, also this, such that everything commutes. And this is just uniquely determined by a decomposition. Therefore, we don't like to write it down. So the cone would be something like this, and it should be the best cone, meaning that for any other cone like this, uniquely you have this. So this guy is called pullback, right? Pulling back this along this guy would be this guy, for instance, right? And so we computed limits everywhere, but because we are interested in toposes, and toposes are set-like categories. So here we also computed everything. One was just a singleton set. That's important to be just a singleton because then you have just exactly one maps. This guy is just a product of sets with projections. And if you want to know what this guy is, it is just simply if three sets, two functions, that D here would be pairs in A times B such that not all of them, such that these two guys are equal. So meaning f of A equals to G. So you can see that this with projections to A and B is just a pullback. So that's limit, finite limit. And to check the existence of finite limit, as you maybe remember, it is enough just to check pullback and one, for instance, or product and equalizer that I didn't write it down. Maybe I have to also recall it because we need it later. So the other one is equalizer. So your D is just these two maps. Then the cone would be what? Would be one map, one to this, one to that, such that blah, blah. So then the second is not needed. Therefore, just one map such that equalizes these two. And it is the best that does it. So if you have another one, then you get a unique map here, right? So, and here in set, it is obvious that it would be just, if it is A, it is B, F, G, you want to compute C. C simply is just a subset of A, where these two guys are equal. Right? Why not? So this is limit. And now the second structure that I need in the topos is it clear, right? Of course. So the second guy was exponential. And what was exponential? Where are you? Exponential. Exponential is just the abstract version of the function space, right? And so the definition was this, easy. So you have two objects, A, B, and then C together with a map like this, that I call evaluation, is called exponentiation. So think of C as the set of all functions from A to B, right? And this is just the evaluation function. And this is the best in that property, meaning that for any other D and any other map like this, there exists a unique map from D to C. Let's write it like this. Say F hat such that F hat times identity A, which is the canonical map here, you have this commutation. So simply I'm saying that you have evaluation and if you have a function from D times A to B, then it induces a map from D to all the functions from A to B, right? Okay. So topos should, of course, in set, it is just a set of all functions. This is just the usual evaluation. Is it clear, Pavel? It is a map. So just the name is evaluation, but the data is just C plus one map like this. That's what I call evaluation, such that the given data is AB, and the exponentiation that we like to write B to the A, for instance, is just a pair C and the map evaluation. Right? So a topos should have these two. Of this guy. Yes. So it is C should be the set of all functions from A to B. And evaluation should be just the usual evaluation function, meaning that you read the function f, A, this is f of A. Is there I guess yes. Yes, but it would be just very, very complicated. So these two are the guys that we had. So if you have these two, the category is called CCC, Cartesian closed category. This is the closure part. This is the Cartesian part. Doesn't matter. The last is he has sub-object classifier. That I have to explain. And that's not fair to say, but kind of. You can say roughly that the whole power of being a topos is here. The rest is important, but not that much. There are millions of categories with these two things. But this guy is just extremely powerful. So to do that, we have to know what is a sub-object. So I have to recall sub-objects. Also because we need it in a serious way later. So what is sub-object? If an object in the topos is a set, then sub-object is a subset. So simply it means that what is a sub-object? Let me check. A monic map, exactly. So a sub-object, so let's say A is fixed. A sub-object is just a map from some B to A, like M, such that M is monic. And monic means so what is the one-to-one function, right? One-to-one means this, right? Monic means the arrow theoretic version of this. So X and Y are arrows to B. So for any X and Y, say C to B, and this is your M, if M O X composition and M O Y equals, then X equals. That's monic. And then any monic is just a subobject. The important thing about the subobjects is that there is order on subobjects. So if you have two subobjects, B and C, and usually people write this like that it is monic. What is the order? The order is that I call M less than N when there exists a map here such that you have the commutation, right? So you can think that this is a bigger subset of that one. And the bad, of course, this guy is, you can check easily that it is reflexive and it is transitive, that I don't write, right? But not symmetric, not anti-symmetric, right?
Does the arrow from B to C also need to be monic?
It will be. Even more, it will be unique. A unique monic. Right. So yes, and this guy is transitive and reflexive simply because you have identity, and if you have this guy and that guy, you compose. That's easy, but it is not anti-symmetric, and therefore it's not a poset, all subobjects with this. So people sometimes make it a poset, so up to equivalence. So equivalence on M and N is simply when M is less than N and N is less than M. And then there is the poset would be denoted by this. So the elements here roughly are just the classes of M is a monic from, because everything is A by B, sorry, from B to A, right? The classes and the order induced. So that's it. And what is subobject classifier now? So one property of a set, it is the poset of all classes of monics, and class means that if two things is, in this way, then they are the same. So whenever I have two monics, such that there is a map here and there, then I call them equivalent.
So a single subobject array, one of these.
No. One of the B's and the arrows, but up to that order, up to that equivalence relation.
Sub A class of subject values.
Exactly. If I don't use that thing, for instance, in set, then all one-to-one functions are there, and it is just too big, because for any b, I have one-to-one function. I could have, right, for some at least, but and I can change it. It's just a proper class, because I can change the name of b. But this means that up to isomorphism, I consider them, and now it is just a small set. Okay, no.
Are you allowed to write separation notation?
Yes. Yes. I'm doing this, right? We are not that orthodox, right? That in meta you have to be also category theorist. So the main kind of property, as I said, in set is that you can classify being a subobject like this. So if you have a subset like this, right? In set, we know that any subset is kind of equivalent in some reasonable way with a map from A to 0 and 1, the values, right? It's just a characteristic function. So how to write this guy in a categorical way? Here it is. So you say that for B to A, sorry, there exists a map from A to 0, 1, and also from this singleton to 0, 1, there is a map. The map is called T that picks 1, the truth, such that this guy is fullback. And this map is unique with this property. What I'm saying? I'm saying that you are given a monic, right? A subset. I find this characteristic function. And the relation between the two is simply that if it's a characteristic function and it picks 1, then this pullback simply is just the inverse image of 1, right? And the inverse image of 1 should be B. So the connection is that you have M here, you have, say, character of M here, and when I say that this is a character for M, simply when the inverse image of 1 is in A is B, right?
Sorry, I think this is what you're explaining. In set theory, each of these arrows is a function.
Yes.
So bottom is a characteristic function of A.
Mm-hmm.
This T is just picking out 1.
Yes.
So what is the top function? Top arrow.
We don't know. So the point is that the definition says that this guy is a characteristic of that guy, right? When M is the pullback of T along this map, and this would be just automatic there.
Giving what's the definition of characteristic function?
Yes.
But sorry, I interrupted you. You said again what the thing was.
I was saying that this guy, Km, is called the characteristic function of M when if you pull back T, it is given, right? Along this chi of M, you get M. Or if you like, there exists a map here such that this guy is a pullback square, right? The map T picks, it is just from one singleton to 0 and 1, right? So it means just picking one element here. It picks 1. So it's the truth, right? So this is just the value, the set of values, and also you have to pick 1 as the truth, and T does that. Yes, singleton star or any singleton, because all of them are equivalent. It can be, but it is just one. It is not any map. It is just one map, the map that picks 1.
Yes.
Why?
So what is the situation when it is 0?
It cannot be 0. Right? There are maps from star to 0 and 1 that pick 0. I don't have to. I don't have anything to do with them. Yes. It depends. What do you mean? So T is just one map that always picks 1. But of course, there are other maps, and we don't care. No, picks this guy. No, picks 1. No, T of star is 1. I mean, yes. Exactly.
If it's
Yes, such that this guy is a pullback.
well, still, so in the case where B is the odd numbers and we're separating,
Uh-huh.
and A is all the integers.
Yeah.
And what is the other function?
Okay, so technically this is just one unique function because it is star, and you cannot do anything, right? It is constant function. Always it's a constant function.
But then if you go around the top of this, everything goes to 1.
Yes.
And go on the other side, everything goes to 1.
Yes.
So
So the being a pullback simply says that B is exactly the ones that go to 1.
well, okay, but it shouldn't be
The maximal one.
Top exists.
Huh?
It has, if it exists, it has to be surely the constant function always exists.
Yes.
So it's.
It's-
Could you give it a name, or is it, does the notation give it a name?
That's the name. Yes.
So the condition really is that this B is a pullback.
B is a pullback. Yes.
So that there's
Of
no
this element.
bigger or smaller, even better.
Yes.
thing.
B consists of the things that goes to 1 via that map. The characteristic maps it to 1 because of the commutativity, but it is the biggest one. So it's all of them. It's just the inverse image of 1, really.
It's still the definition here,
Mhm.
not defining B, defining the property of this chi-n.
Yes.
Okay.
So I'm just defining when I say a map from A to 0, 1 is the chi of this monique. But then the sub-object classifier axiom says that for any, which is, a property of set, it says that this guy, this object is a sub-object classifier, meaning that for any B, the chi exists and it is unique. Right? So let me just write it down here. No, for any B, no. Let me write it down. So what is a sub-object classifier? A sub-object classifier is one object, omega. Right? It is omega. This guy plays the role of 0 and 1. And one map T, the truth from 1, this is the singleton, to omega, picking truth, such that, so this pair is called sub-object classifier when for any A and B and any monique M from B to A, there exists a unique map, say chi, from A to omega, such that, so unique in that property, such that this guy is that is confusing. It's this is confusing. Sorry. Such that this guy is a pullback. So in a categorical term, simply I'm saying that there is a set in quotation of values such that it has one true value, and it classifies all subsets such that if you have a subset, you can write it as the inverse image of a map to the values. So to any A, I assign a value of being in B, right? Which is 1 if and only if you are actually in B. That is the last one. So if you have all the three, and we saw that set at least has all the three, and not just set, so maybe the obvious examples are of these guys. We saw set has all these structure, so it's a topos. We saw we can check actually finite sets also has the property because just finite limit, so why not? And 0, 1 is finite. And another one is just the category 1, which is just one object and one identity morphism on it. So you can check that it has also all the properties. It is just the degenerate topos, right? So we saw these guys. Okay, so is it clear what the definition of a topos is? Why not that guy? I forgot that I have. Okay. At least finite sets, yes. Yes, you can construct all. Okay. So that
finite sets embed into every other topos, which is not the trivial.
Yeah. So the thing is that finite sets, yes. Yes. Finite. If it is finite, we can construct every because they have co-limits and the co-limits are disjoint, so you can construct all finite sets. There, yes. The answer is yes. It embeds, but not set, just finite sets. Yes. Okay. I guess that's what I mean. So now the next thing that we did was constructing toposes, right? Because we need this guy to do something with, and we construct. I said that I can explain 3 ways to construct toposes. We covered one in 2 phases, if you remember, and the second and the third are remained, right? The first was this. So the first that we saw, the only one that we saw, maybe, and the first phase, so phase 1, was this. That if you start with set and you construct set to the C, where C is just small category, and this guy means that the objects are all functors from C to set, and the maps are natural transformations, this guy is always a topos. We checked all the structure, all the limits, exponentiation we constructed subject classifier that I don't care, the exact structure. But the main thing is that it is a topos, right? And there are some examples that you may like. So if your C is just a category 1 with one object, etc. So this is just the usual set. If your category C is 0, the empty category, then this is set to empty, and you can check that it is actually equivalent to this one. So these 2 examples are of this sort, right? They are set to the C. The other that we checked all the time was if you have one object and one group as maps over it, we saw that set to the G is simply the category of G actions. Maps are the ones that respect the action. The other that we saw was that if C is just one abstract map, or if you like, just the order 0 less than 1, then we saw that set to the C is just the objects are functions between A0 and A1, and I called it a variable set, a set that varies over time, and time has just 2 moments. So this is what you see at 0. This is what you see at 1. This is the evolution of the function, if you like, and then morphs of set to the C here in this case was just if you have 2 objects, two variable sets, if you like, then map or just two maps for 0, 1, such that you have the commutation, right? And probably the last one that we saw was that if C is this category, it's abstract star category, two nodes, two maps, then set to the C, which is also, of course, a topos, is just a category of all quivers. What is a quiver? A quiver is just a graph, multi-graph. So between any two vertices, you can have many edges, and it is directed. So, and the morphisms are the ones that respect the connectivity, of course. And this is just the category of quivers. We saw all the details, but if you want to see anything, just ask. So these are some examples that we played with somehow before introducing the main guy, which is the set theory. And we think of the elements here as sets variable over time, and C is just a category of time. Nodes are temporal points. Maps are the ways that time evolve, right? Okay. So, and I said that I don't like this guy. Very beautiful, but it is not enough, right? And do you remember why? What was the problem? Three problems, exactly. Yes, the first problem is easy to explain. The first problem was that the logic is always intuitionistic. We want it to apply for classical theories to prove independence. Why? Because the set to the C is set-like object, 1. 2, we can see, and I will explain just roughly, that you can interpret kind of the whole mathematics inside it because it is just set-like. But the problem is that the logic is not classical, this is intuitionistic. What do I mean by that? So if you have a category E, right, we saw that if you have one object A, sub A is what? Is a poset, right? And the structure that you have on this poset is kind of your logic, right? Because why? Because what is logic? When you write logical things, you write some predicates and conjunction, disjunction between them, blah, blah, blah. And so when you want to interpret it inside a category with enough structure, you have to pick one object as your domain. Usually we do it in set, picking one set, and then subsets would be just the predicates, right? So in arbitrary category, you have to pick one object. Sub-objects would be the interpretations of subsets of predicates with one variable. If you have two variables, then sub of A times A, etc. Therefore, this guy is important because the laws here are the laws of your predicates, right? And the problem is, the good news is that whenever E is a topos, I didn't prove that, I just claimed it, and I won't prove it because it is just tedious. Always, for any A, if E is topos, for any A, sub A is a Heyting algebra. That was my claim. And of course, you don't remember what Heyting algebra is, right? No, right? So, recall. Heyting algebra. Heyting algebra is H is a Heyting algebra. So what's the Heyting algebra? Heyting algebra. So this guy is a poset first. So a poset is a Heyting algebra with when you have this property. So H has all finite meets and joins. I will explain what it means. H has Heyting implication. And that's it. So categorically, we know these guys. So here I'm simply saying that a poset is a category. So H has all finite limits and co-limits. And here I'm saying that H has as a category exponential, as we saw before, right? But that's just too mouthful, right? So because, come on, it's a poset, we can write it down in a very concrete way without arrows, etc., right? And if you do it, it would be just simple. The simple definition is this. So finite limit. Meet means just product here, and join is co-product. So what I'm saying simply is, and that this is very important thing. So just keep it in mind. So meet means that for any AB, okay, first, there is terminal object, right? So meaning that there exists top element 1 such that for any A is less than 1. This one. 2, meet, so for any A and B, product exists, meaning that there exists C, such that C is less than A, C is less than B, and it is the best, meaning that for any D less than A, less than B, it is less than C. So this C is written like this, right? The meet. And dually, you have to have for all A, 0 must be less than A. So this is your top, this is your bot. If you think logically, you have joined the dual of this, meaning that A, I'll write it like this. So A and B, both of them are less than this guy. And this is the least with this property, meaning that if A is less than C, if B is less than C, then A or B is less than C. These are just the usual rules for these things. And then if I simplify the exponentiation here, it would be for any A and B, you have something like this with this property, the C and A is less than B, if and only if C is less than A implies B. Just the usual intuitionistic implication, if you like, right? So this we can accept as intuitionistic implication, but that is just modest moment. C and A is just A and B and A, which is less than B, right? So if you have a Heyting algebra, I would say that you have access to intuitionistic logic because the rules that govern this guy is just intuitionistic logic. And so now we can come back to this guy. It says that if you have a topos, pick any element, any object A, the sub of it, which is a poset, is a Heyting algebra. Meaning that if I have two sub-objects, I can meet them as intersection. So there is intersection of them. There is union of them, which is the join. There is the whole as a sub-object A. There is empty, which is the 0. And for any two sub-objects, there is some implication between them with that property. Right? In set, this is, we know it, right? In set, if it is set, the sub A, in set, sub A is a Heyting algebra, and then, of course, because subsets you can intersect, you can union. But what is this guy? If I have two subsets, say U and V, what is this? It is just U complement union V. The usual Boolean negation, right? So simply I'm saying in the Boolean word that I have complement operation. But this is just a fancy version of it without those properties. It's just minimal version of that. So you have access to some sort of complement, the union, intersection. So that's good because then it means that you can interpret some logical properties in your topos. The problem, though, is that this guy is a Heyting algebra, not a Boolean algebra. A Boolean algebra is a Heyting algebra where A or A to, this is just negation of A. Sometimes people write this, is 1. So either the complement, which is the negation of A, really complements A. So both together completes the whole subsets, right? So if you have this property, it's a Boolean, it's like the classical word, right? So simply it says that for any element so if your A is a subset of A, right? Then this simply says that any element is either in A or its complement, right? This is just the usual classical word. And the problem is that this sub A is not classical, it is intuitionistic, and I cannot use it for the classical purposes. Sure.
Is it easy to construct a Heyting algebra, which is real algebra?
Yes, very good question. So pick any topological space, define the Heyting algebra of opens. Of course, union intersection is of course available. So the question is that what is this guy? It is just the interior of U complement union V because it should be open. And then you can check that it has this property. It is really a Heyting implication, but you don't have it. Usually you don't have it. Why? Because say X is just the real numbers. And U, this A here, is just say minus infinite till 0, right? And let's compute U implies, so negation U, right? Negation U is just U complement, union nothing, but the interior of it. The interior of it is what? Is 0 infinite. And both together does not cover 0. Yes, but it's negation. So negation means U implies empty, so V is empty. Here you mean I have no, that's right, really. So it is the interior of the whole thing. Because U complement is not open, right? It cannot be open. No. So you think it should be interior of U complement union V. But I know it's not so. In my example, V is empty, so yes. No. So in my example, negation U is U implies empty. U implies but. Here. V. Union V. It is U complement union V, the interior of the whole thing. And in this example, negation U means U implies empty. If you compute it, it would be U complement union empty. It doesn't mean anything. We first do the classical one, then apply the interior. So here the classical is just a complement. The interior eliminates 0 because, right? So the union does not cover 0. So more or less any interesting topological space.
And this Heyting algebra with real numbers, you can. Is it true that ontologies in intuitionistic logic can be tested on this?
Of course, they can be tested, but it should be complete, right? So yes, for real numbers, yes. No, for finite, no, because of course you can just play with this. If you have all finites, then yes. Not really the minimum because there are many examples of complete things, so this is just one of them. Yeah, yes, kinda, right. Yes. There's a theorem that I don't remember if the space is metrizable and I don't know, blah, 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 some very basic conditions, then it is complete. And R is one of them, the contour space is one of them, the bare space is one of them. So there are many. Okay, so what I am saying is that you get your Heyting algebra, you get intuitionistic logic, but not necessarily classical. And that's kind of bad for our purpose. This is one of the problems that I don't like set to see. The other one was kind of too hard to explain, but probably I have to. So maybe that's also helpful if I say that if I use some small c. So if your c is just this order 0 less than 1, right? Then any a is just a set that's variable, and then you can okay. So I'm trying to find a good example. So c is this. A should be just some variable set, and the variable set simply is star. It is just a singleton that varies over time, so it does not vary really, right? And then the sub objects here, let's compute sub A. Sub A are what? If you compute it, and I don't, of course it is, so let's write. This is B0, B1, and so you have maps to star, and these should be Munich, right? I'm computing the sub objects, right? So we did it before, but anyway. So simply you have to pick a subset here, a subset there in a compatible way. So meaning that a subset here is either empty or star. If it is empty, it doesn't matter. If it is star, then also above you have to pick the star, right? So how many subsets, how many sub-objects we have? Either empty, or the whole set. These are just the usual classical one. The whole, the empty, right? Of a singleton, say. But you also have another one, the third one. The third is empty star. All right. So the sub-objects, there are 3 of them. So they capture the idea that either you pick star at the beginning and keep it, or you cannot pick it and you never pick it, or at some point you pick it later, but not now. So you have 3 values. And if you compute that, this guy, the 3 values, it's a Heyting algebra, which is not Boolean also. Right? Simply because it cannot Boolean. That star, that bad guy, the middle guy, that you pick a star here, it has no complement, right? The complement in a Boolean way. Right? So it's linearly or this. But just as a coincidence, it's not usually like that. So. Because I have, I have no. That is linear. So that's the point. C is linear. If C is not linear, you have branch, then you can play with this, right? Pick a star here or there or both or none because they are independent, right?
I think set that I just think the prima and model that if there's a finite set, will it be if I think algebra?
Oh yes.
Yeah.
Yes.
It's example important because I didn't get
Yeah, not really, no. No. Yes. So but I can say something. So you know Kripke models, right? So what I'm saying is simply just the Kripke model version in the categorical language. So simply I'm saying that you have this Kripke model, right? And some atom P, say, which is not true here, but true there. And so in terms of P, there are 3 things that can happen. Either PP, no P, or just P here. These are the three possibilities, the three values. So this is what I'm saying. And also, if you have any poset and P offsets of the poset, it's a Heyting algebra, which is usually not Boolean, right? Just the KitKat style or a forcing style things. So, okay. Then, the second thing. The second thing was hard to explain, but come on, we have to do it. No, no. It is Heyting algebra. Yes, the opposite. So technically it would be this. So let's say that you have 0 and 1, and 0 is less than 1, right? And then the Heyting algebra is this. So empty 0, 1, and the 1 in between, right? And the order between them is just a subset order. This is Heyting algebra, but it is not Boolean. It is not Boolean exactly with that example that P can be true later. Yes, yes, by inclusion. Exactly, chain with 3, yes. Yes, it's Heyting algebra which is not Boolean. Kinda it is the smallest possible one. Exactly. Which is bad, right? So,
What is a statement which is true in this Heyting algebra, but not in the big one or vice versa?
big one, which one?
So how can I, using logic, how can I see difference between this Heyting algebra and that Heyting algebra?
Ah, yes. So that's tricky, but usually you can write some formulas that capture the depths or the widths or something of that sort. And whenever it is finite, then that thing, it is like the usual model theory, right? In finite model theory, when a model is finite, you can write a formula that captures that you have at most 5 elements or 6 elements or something. You can do kind of the same thing here. It is tricky, and I don't remember it.
Distinguish any finite, non-isomorphic Heyting algebras?
No, because the definability is up to elementary equivalence, which is by simulation here, not isomorphism. Exactly like this, the usual classical setting, right? Okay, fine. Sure.
Question about notation. A here is a category, right? So
A is an object here.
oh,
C is this guy. It's a poset. Then I'm thinking inside set to the C as a category. A, which is this guy,
I see.
is the object. Okay. Okay. So if you find this hard, then we are going to something unbelievably hard, right?
Sorry, this is all the first 3 reasons why.
No, the first phase of the
First phase.
no, sorry, yes, you're right. The first reason that's why I don't like this set to the C, and the second reason is something from geometry. It doesn't mean anything really for us, but the point is that I need the intuition to explain the construction afterwards. So, and this is what we did. So I said, if you remember that if you change set, if you work with set to the C opposite instead of set to the C, which is not important, right? So, for set to the C, the intuition is that over C set close, right? For this guy, the intuition is that elements, objects here, they are just functors. They record some sort of maps to some space, right? So the idea was that C is think of it, but it is not really the case, that it is the category, some category of simple spaces in any sense of space that you like. You can think of, I don't know, triangles in some flat space, or just flat spaces, or whatever, right? Opens of R, something that you relatively think it is simple. with their maps, right? And then I asked you, if you remember, that how, when you have a category of simple spaces, how to construct complex spaces, right? Let's say that how to construct the sphere, the Earth, from just the simple flat things. The idea was that you record all possible ways that you look from simple spaces into the complex space. So it was like that, this, if it is the complex space, and you have the word C of simple spaces, something like this, right? And the maps between them. So pick any element here, all the images here. So this is the things that you can really see, because these are the lenses that you can see through. And all the maps here, record them inside the functor, and then that functor encodes this big object. What do I mean by that? So for any A, we said that think of f of A, which is a set, as the set of all maps. Oh, everything here in the quotation is just informal, right? All the maps from A to the space, so some space X, and this is f of X, right? So assume that you have some space X, pick all the maps, whatever it means, the set of all the maps from A to X, right? And then construct this functor, f index X. And this functor kind of encodes the whole local data of your space X. Now, the conceptual leap is that maybe there is no X out there, because what does it mean to have X such that for any A you can compare them and there is map between them? It doesn't mean anything, right? So you can think that, okay, just forget and pick any functor that you want and think of it as the set of all maps from A to some space that F is encoding, right? This is what we had. And this is this is the geometric intuition of thinking of these guys that are also called pre-sheaves over C, another name. And so that's good. So therefore, we can think of this guy as all the generalized spaces, all the functors, general spaces based on the test spaces in C. That's good. But the problem is, no, there is no problem for now. But I can explain something, and then the thing that I have to explain is this. One example helps, right? So one good example that people love in geometry is this. They start with some topological space and pick C as the opens of that topological space with this order, right? This is a poset, right? You pick C as this guy, and then set to this C, right, opposite. One of the objects here, for instance, is this guy. That realizes that idea. So what is the object here? That A is U, some open subset, right? Open of X. And then pick here. So I said that it should be all maps, right? All, say, continuous maps from U to R, right? That is capturing R, right? Via the test spaces here, by all the maps, and by map here, I mean continuous maps, because we are in continuous geometry kind of thing, right? You can change from continuous to, I don't know, differentiable. For instance, if X has some differential structure, then you are capturing exactly the same object R, but via differentiable maps, right? So what I'm saying is that the notion of map is kind of, it can change here. So this is one of the interesting examples that people like, and many other modifications of it. We will come back to this guy later, but another one is, if you remember, I said that So C is here. It is just a word of simple spaces. And there is some bigger guy set to the C opposite of generalized spaces. And if you remember, I said that we can embed this guy exactly somewhere here. So for any A, you can assign a functor that was the Yoneda of A, right? And what was that? Yoneda of A is exactly what we want it to be. So this, right, intuition was that it should be all the maps from B to the space A, right? But it means it means something because we can have it in C. So you can say that all the maps from B to A. So this Y of index A is then a functor from C opposite to set. So it leaves here, and then we saw the Yoneda embedding and the Yoneda lemma that I don't recall. The whole thing was that actually this guy sits here, meaning that first, of course, you can map A here, or any map to a map here, such that two maps go to two different maps, so there is no collapse, and no new maps here. So any map here comes from a map there. So it really embeds there, sits there as some part of the generalized spaces, right? So we saw this, and then I said that there is something that I don't like. The thing that I don't like is there is something good about this example, and which is not true for all functors. And the good thing was that when I say map here, map is something locally defined, which is not usually true. Locally defined means simply that if I have, if I cover my U with some UIs, right? So this is my U, this is say U1 and U2, whatever, I don't know. Then if you have some functions on the parts such that they are compatible on the intersections, you can weave them together to get a new function, right? Because locality is just, continuity is just a local notion. If I change the continuity, you remember, with boundedness, we bounded, then the same is not true, right? Because it is possible that locally functions are bounded, but altogether it is not bounded, right? So the geometers like this being locally defined thing. Differentiable is local, continuous is local, everything is local. So how to axiomatize this? How to push? How to say stratify this guy or limit all the functors to the locally defined ones, right? So for that, you need to introduce first some abstract notion of union, and then try to mimic this idea that if you define something on the parts such that on the intersections they are compatible, then you can extend it uniquely, right? And this brings us to that notion of shift that we had. So first, what is the axiomatization of my union? And then I explain why I need something like that. So let's say C is a category. You can think of this category if you like. And then J is some operation such that to any object A, it assigns a family of maps going to A, not just one, some families of maps going to A, right? So something like this, that some families going from A1, A-N, blah, blah, to this, just some of them. And not in arbitrary way, in the following way. But before that, I have to say that what is the intuition? The intuition is that these are subsets of A that cover A. So the intuition is this, and the definition is that you have to pick some family, but not any. It has to have the following property, that for any A, for any covering family, for any map B, there should be, so this is for all this, for all, everything is for all here. There exists something covering over B, like BJs, AIs with different indices, such that any BJ composed with this can be factored through one of the AIs. So it exists, right? If you find it very, very, very weird, it is not actually that weird. So simply it says that if A is union of AIs, if you have the cover, and B is a subset of A, then you can cover B via parts that are inside A. And we know how to do it, right? So you can cover B by B intersection AIs. Any B intersection AI is my BJ, which is less than AI, right? But you can cover your B. So the notion of coverage means that everything is smaller, you can cover it. And then we saw some coverages, if you remember. So one coverage is just this guy. The union as coverage, so some subsets cover if union covers. And you can generalize it. I need it later. So you can change X to a complete Heyting algebra. So let's say that your C is L, let's say L, okay. And L is complete Heyting algebra. Complete means that you have all the limits. So all big joins or meets. And then define J of A. A is one element in L such that I say a family, say, of B of AIs, A1, etc., AN. It's a covering family if and only if, so it is in J, if and J of A, if and only if there's the union of AIs is A. So it is just the lattice theoretic version of this, right? So just forget that they are opens of something, just subsets, and then as long as you have the infinite join, that's enough, right? So we saw this guy before, and we also had this J as J of A is empty. So just nothing is covering. J of A is all families of maps coming to A. So any family that you pick is a covering family. It's another one. And the one that we kind of like for some reasons is just the dense covering. So I have to define the dense covering. What is the dense covering? The dense covering is this. So C is just arbitrary category, and you have A, and you say that some family A1 blah blah can be infinite. It is covering if for any B there exists one of the AIs and one map such that this guy factors through B, right? Which is kind of weird. You have to check it is a covering. We did it. I won't. But maybe the example that I used before helps. So if for C you have just this tree, right, something like this, then as a poset, right, in the converse relation, then I say that's pick all the minimals, all the maximals, it depends how you read this tree, all the maximals, say, like this, that cover your node, and then call it the coverage. So that's the dense family. So for instance, this covers, these two covers this guy, and this guy is covered by these four, right? And it is exactly this definition, right? So it says that these two cover this guy. When for anything else, I have nothing else. So let's use this. That's better. No, good. But there's nothing that I can use because it is stupid. Anyway, let me add one node here. So these three cover this guy, right? And this is exactly this definition when you forget about the maps because it is order and maps are not important. And the reason simply is that it simply says that the tree cover the guy when for anything else, like this guy, right, it is less than something and it is less than 2, right? So technically, they are all possibilities above. You cannot just escape all the end possibilities. So why is it important? Because later we see that when we restrict to sheaves, that I will recall soon, with respect to this dense coverage, then the category of sheaves with dense coverage, it is a topos. And for any object A inside, if you consider sub A, then it would be a Boolean algebra. Not just a Heyting algebra, like in any topos. It would be a Boolean algebra. And this is the reason that I care about the dense coverage, because adding coverage gives me the classical setting. So adding coverages actually and restricting to sheaves solves both of my problems at the same time. The classicality I reach via this guy, and also the locality I reach via, because I have the union, but I have to explain what sheaves they are. So, and you can see the classicality essence here. So I explained before, but maybe I have to do it again. So why I say in the classical world that these two guys cover this, or these four cover this guy. So think classically that this tree captures P, negation P. So if you go here, P is true. So PQ, P negation Q. So negation P, Q, negation P, negation Q. Right? So all the possibilities. So these maximal guys are total assignments. These are partial assignments, right? Here there is no assignment, here is P1, P0, but these are total. So simply I'm saying that if you are here, this covers all possibilities for you in the classical world, because above either Q is true or is false, right? So if you know, because later you at last when you go up and add and add and add, at last you cover all classical possibilities, right? And therefore you can say that, you know. Anyway, yes. So let's say that C is a category, whatever it is. A is an object. A family of morphisms into A is called covering with respect to dense coverage when for any B and any map, this map, so there is some I such that the map AI to A is factored through B. So these are just the end maps somehow that any other map goes via them. These are the end nodes. This is dense. No, coverage could be anything with this property, but this is just one, which is just a dense coverage. One coverage between all. Yeah. Yes, yes. So these are, say, via the maps, these are all the possibilities above A. Okay. So what is a sheaf then? So that's the coverage. This is just the the generalization of the notion of union of the covering thing. And then now you can say, if you have C and one coverage, which the package is called a site, right? What is a sheaf with respect to a site? So a sheaf is just a pre-sheaf. It's just this guy. When you think of it as, the general space, such that f of A captures all maps, but all local maps, not all maps, whatever it means, right? And I have to put some condition on F such that it sees that these are local maps, like the continuous example that I had here, not like the bounded one. So, and the condition is just a sheaf condition. It simply says, as you imagine, that if you pick A and you pick AIs, and this is a covering family with respect to J, of course, for any covering family, if you have, so you apply your F, let's say, on this, it would be F of A, F of A1, F of A2, etc. And F is just contravariant, so it should be something like this, right? Then, if you have a family of X2, etc., in each of these two, these are all sets. In each of these sets, if you pick one element, you get a family, right? Xi in F of A I for I, right? So some of these families are compatible families. What do I mean by that? So the intuition was that X1 in F of A1 is just a map from A1 to the space. This is from A2 to the space, right? So they are compatible when on all the intersections, they are the same. So how to write it down? So the family like this is called compatible when for any I and J, for any two maps from this guy, and any B such that it is in the intersection, so it commutes. Then if you compute F of it, you get this, right? And here you have Xi, and here you have Xj. They are compatible when they go to the same thing here. This map is kind of the restriction to the smaller one. The restrictions are the same. If you have this property, which says for any ij, for any b, such that the guy computes, then xi here, xj here, they go to the same thing, then I say that this family is compatible. Then the sheaf condition says that for any compatible family, like this, any compatible family, there exists a unique x here, such that everything here comes from that x, right? So it says that if they are compatible, you can glue them together on A, which is covered, in a unique way. You can glue them and in a unique way. So unique means that the whole information is local in X, right? If you know it locally, then you know it. So for instance, you can use it to prove that two things are equal in F of A if they are equal on a coverage, right? The whole information is local. And also you can glue it, not like the bounded case. If you glue them, you get again a function. So therefore, then if F has that property, I can say that F actually encodes on locally defined maps, not all maps, right? In some vague sense. Then what is the category of sheaves? The category of sheaves is just a full subcategory of all pre-sheaves. What is it? It is this. So assume that you have a site, then you define the category of sheaves as objects are sheaves. sheaves in this sense, right? And morphisms are just natural transformations, as in pre-sheaves. So then you can see that this guy is actually a subcategory of pre-sheaves, which is this, also denoted with this, right? So I pick some objects, but morphisms are just the same. So I'll pick all the morphisms. I don't care, right? That's the category of sheaves. So this is the second phase, going from pre-sheaves to sheaves. But I have to say that this is not a restriction, really, because J is the thing that you can change. Actually, you gain more categories. One of them is this. So we saw it before, that if you put J as the trivial, the one with no covering family, then it is easy that since you have no covering family, you have no condition. The sheaf condition disappears, right? And therefore, all pre-sheaves are sheaves if your covering is just that trivial covering, right? So there is some J such that all pre-sheaves are sheaves. There is also another J, that J, this is the empty one. This all morphisms, this is the maximum condition that you can put on sheaves. And you can compute that for that J, there is just only one sheaf, the constant functor that goes from C opposite to set and picks just the singlet. It is just category with one object. It is just that one that we had before, right? So there are many categories. So what I'm saying is that this guy is also one of the sheaf categories. It's not, yes, on the at the face of it, it is just subsets, but not really. So then, not everything is a sheaf. We saw it before, right? That the example of bounded things. But also, if you remember, we had this constant functor that goes from set the opposite to set, and A is just a set. And delta A of any no, A is X is a set, delta X of any object A is simply defined as X, right? Just it is fixed, so it doesn't change. And all the maps are identical. So we saw that this guy is a sheaf, and it doesn't matter with which coverage, if and only if that X has one element, right? If you remember. So as long as X has two elements, then no. Okay, one way is true, but it really depends on J, but anyway, sure. So not everything is a sheaf. The last thing I remember that we had was that, okay, sometimes something is not a sheaf, but you can make it into a sheaf. So the idea is that if something is not a sheaf, it means that there are some compatible families on some coverage such that you cannot glue them together, right? More or less. So add the glue, because the glue is missing, right? The new function is missing. Add it to the city, right? That is called the sheafification. That simply says that C and J is a site, F is a pre-sheaf. It is possible to assign to F something that's called A of F, associated sheaf. It is now a sheaf, of course, with respect to the site, such that it is the best possible sheaf, meaning that you can go, there is the canonical map from A to A of F. So it is kind of the expansion of F to be a sheaf, but it is not really monic. It can be anything. And it is the least possible way to do it, meaning that if I have another sheaf and another map, say alpha, then there exists one alpha hat uniquely from A of F to E, right? So it is the least possible sheaf that you can construct from F. You make F to a sheaf, and it is, it's like the closure property, the closure operator that any other sheaf is just bigger than this. And this is also important at some point when you cannot do the usual things. You do this. So if you remember, we had this, that if you have the limits, if you compute the limits of some sheaves, it is also a sheaf, right? So if you start with sheaves, then product is a sheaf, right? Pullback is a sheaf. That's good. Therefore, the category of all sheaves has all finite limits. And you can compute it as they are pre-sheaves. And why is it important? Because as pre-sheaves, the computation of limit is pointwise, as we saw before. So then that's good. But the co-limit is not like this. So it is possible that you have E and F as two sheaves, and then the coproduct of them is not a sheaf. Actually, we saw one example already, right? So the singleton one, the constant one, is a sheaf, and 1 plus 1 is just constant 2 everywhere, which is not a sheaf necessarily. So then whenever you have the problem, apply the sheafification. Usually it works. So for instance, this is really the coproduct and E and F in the category of sheaf. So if you remember, in the category of sheaves, we showed that the exponentiation is also a sheaf. Exponentiation of two sheaves is also a sheaf. Therefore, the category of all sheaves, like the category of all pre-sheaves, has all finite limits, has the exponentiation, and the sub-object classifier is different. We constructed in both cases, as far as I remember, for sheaves and for pre-sheaves. And therefore, we can finally say that this guy is a topos, right? This is the first construction that we had. And I have to say something else, that these guys, they are called Grothendieck. These are the first toposes. Any category which is equivalent to a category of this form, for some C and J, it's constructed in this form, is called a Grothendieck topos. So since pre-sheaves are also sheaves for the trivial J, therefore all we had before, like the G sets, like the set to, the quivers, whatever, right? All of them, the set to the G's, all of them are Grothendieck toposes, and this is not just some class of toposes. This is just a very, very big class of toposes, right? So more or less, you can do everything that you want here without any need to go outside of Grothendieck toposes. So, but there is non-Grothendieck toposes also. The nonsensical example is just finite set, of course, because finite set is a topos beside it, but you cannot construct it like this because they are just so big. They are either set to the 0, which collapses everything, or set to at least 1, which is just too big. But come on, that's just a very bad taste example, right? There are some very interesting examples of toposes that are not Grothendieck. They are kind of enough for anything that we want, but I want to also to say something about the other two, because computationally they are more important. But if you want to do, I don't know, some sort of forcing, that's enough. So any forcing that you saw that has some categorical version, you can do it by different peaks of C and J's. But if you want some, playing with feasible data, computational data, etc., then you need another construction, which is the effective topos, which is not Grothendieck, and I will explain later. So the other two constructions that I want to continue next time with, they are one, Heyting valued sets. These are just very in the form of Boolean value. People like it in the forcing community, right? To construct models, and they are more logical. So these are more geometric somehow. And then the next one is and so probably I cover both of them at the same time. The second one is something that's called effective topos, which is just the word where it is a set theory where everything is computed by definition, which is kind of good, right? You have a mathematics, you do your set theory, but everything is computed. So these are the two, and then we come back to interpret logics inside toposes, and more or less these guys, and the effective one to prove our independences finally. I guess we have no time, so. Sure.
Last time you used the concept of R,
Yes.
they don't remember.
Maybe it's even here. Yes. So yes, that's the site. A pair of a category and a coverage over it is a site.
Category A.
And a coverage over it. J, the coverage.
Cover.
The-
What is covered?
Oh, yes, I defined it. So what is covering? No, the real name is this. So we have coverage, which is this J, and any J says that for any A, what are the covering families? So the maps are the covering families. But sometimes I may say cover for coverage because I'm lazy. Okay, sure.
So you have site
Yes,
and then
yes. According to a site. No. No. The category of sheaves is not the category of.
The sheaf.
Yes. We define a sheaf for any site. A sheaf is just a functor, a pre-sheaf, such with some properties. The property more or less is that for any covering family, according to J, if you pick elements in F of it, such that in a compatible way, then you can glue it in a unique way. And
a certain object of this kind, F, C, or whatever.
yes, which is called the pre-sheaf, is a sheaf. It's just a function, but it is a sheaf if you have this property as well.
The category of sheet, object, sheet,
Exactly.
and then that's it for the person you cover.
Yes.
Category of sheet over C and J.
Yes, for some C and J fixed. Mhm. Yes, yes.
For all B,
For all B. For all B such that, for all B and two maps such that everything is committed. But if your C has, pullback, this B can be just picked as a pullback. Because pullback is the best one. So if you have it for it, then you have it.
mentioned covering maybe two things before getting to the independence groups.
Oh, yes. But this covering is not that common. So,
Do we need to go through those?
yes.
They used it in the independence.
Yes. Yes. But for some, yes. Right.
Last time you had some examples with continuous functions.
Yes.
Could you go through one example of a sheaf with continuous functions?
Yes, I don't have it now. So the example of a sheaf is this. So you have you fix a topological space X, right? And then your C would be O of X and the order, right? And your J would be just the usual union, right? So I say that some UIs cover U when the union is U, right? So what I'm saying is this. So I say UIs in U, right? These are maps, but simply they are just inclusion, right? I call it covering family if and only if the union of UIs is U. So that is my site then. And now I have to introduce one sheaf, right? So the general example with, oh, this is not the most general one, but good enough. Pick another topological space, Y. It is topological space, right? And then define F, say sub Y, of like this on C opposite, which is just the OX opposite to set, and define F of Y of some object here, which is open, as all continuous maps from U to Y. That is a sheaf. Why? Simply because the elements here are just maps from U to Y, right? Maps over. So the end is always Y. So these are just maps over U. So the sheaf condition simply says that if you have some maps over some U's, such that they cover U, the big one, if on the smaller ones the maps are compatible, then you can glue them together to get one map over U. So that is the example of a sheaf. And if you want to play with it, just change continuous to bounded to see that it is not a sheaf. Or to constant, then it is not a sheaf. Because constantness is not local. Right? Okay. What's happening?